Okay, in this video I'm going to talk about a matrix inverse. So in the previous video I talked about how to the basic operations of the matrix, including the plus, minus, and products, and determinant. So actually, if you talk about the matrix A solid divided by B, because I didn't talk about that in the previous one, there's no such a definition in the A divided by B. Instead, we have one way we can say that is A times B inverse is called A divided by B. So this B of inverse is, if you consider a scalar, is like a 3 to the minus 1. So it's, if you say 2 times 3 is same as 2 divided by 3. That's why it's sort of division. Okay, so we end up having to compute the inverse in this case. Okay, so now I'm going to talk about the inverse. So a matrix inverse talks about the property for a square matrix. So if we have the same number of rows and same number of columns. So a square matrix A has an inverse, which is notation-wise is just you just put A to the minus 1. Okay, here I just tell that this is dimensional matrix is an n by n. You can actually omit this one if you don't want to show the dimension. Okay. The inverse is computed as if A n by n time another matrix, which is n times n the inverse, if is the product of the two is also the same as you change the order, which means you do a n minus n times n minus time n a of n times n is identity. If the product's identity, so I put it that identity over here. Identity matrix, which is a matrix, of course it's still n by n in terms of size. It only has 1 on its diagonal entries and 0 for all other entries. So that's identity matrix. If the product satisfies properly, so it's A n minus n, this matrix is called the inverse of A n by n. Of course, we can also say, so this one should A n minus 1 is also inverse of A n minus 1 is the inverse. Of course, they are A is the inverse of B. Of course, B should be inverse of A. Okay, so that's the definition. All right. So how do we compute the inverse? Okay, there's two ways I'll talk about how to compute the inverse. The first one is called the Gauss-Jordan elimination method. So I wouldn't talk about too much detail about this one. I think if you take the EA1, you should know a little bit about how to compute the inverse in this way. What it basically means is if you put an A, well, if you want to compute the inverse of A, okay, assuming it's n by n, of course. Okay, it's n by n. Okay, so you put a identity matrix which is also n by n on the other side. Okay, put them in parallel on two. If you consider A as columns, I as another columns, like 2 blocks. What we do next is we try to do different kind of operation, including multiply. You only do row operations. You can do the multiplication by a number, for example. You can do the sum of 2 rows. You can do the row switch, for example, but you cannot do column operations. Okay. In other words, if you do operation, you will do operation on both this side and this side. So you do the same kind of change. So when you change this A, the goal is to change the left-hand side to identity. So you do the row operation such as the left-hand side become identity. Then the same type of operation will change this identity to another matrix. This will be just A inverse. Okay, this is what it means. Okay. The second approach is called determinant approach. So you actually can compute the A inverse by using this method. So this is how we compute that. So A inverse is given by 1 over determinant of A. So we already talked about how to compute determinant in the previous video. So check my previous video if you don't know how to compute determinant of A. Then you want to compute the cofactor. Cofactor is something, another matrix. The matrix is actually composed of cofactor of each element in your A matrix. Okay, what it means, I have C11, C12, C21. So pay attention to this. Now C12. This is C21 and CN1. Okay, so each of the Cij over here is actually a cofactor. What do we call cofactor? So what does cofactor mean? It is a -1 to the power I sub j, depending on which one we're talking about over here. Okay. So it was if the C11, let's say if it's C11, it's just -1, 1 plus 1. Okay, of course you still have to compute the determinants of some matrix over here. Okay, similarly you do the same thing for I sub j. So here's how to determine the first part. The second part will be a determinant of a matrix. in fact, it is a n minus 1 times n minus 1, which means it has one less row and one less column than the previous matrix A. Okay, so what it does is try to removing the i's rows and j's column A, because this I is coming from here, j is actually coming from here. So by removing the i's row and j's column of the A, then you have n by n minus 1 of time n minus 1 matrix. Then you compute determinant. You put it over here, then do the product of the minus 1 to the i's plus j's power times the determinant. Then you get the cofactor. Then you put all the cofactors over here, and then you compute the determinant. Then you find the inverse. Okay, that's the second method. The question is, can we always find the inverse of any square matrix? Okay, looks like we can compute any matrix. The answer is no. So if I look at the second determinant method, if a determinant is 0, which means you don't have an inverse of matrix. So in other words, if the determinant of A is 0, A inverse does not exist. So in other words, we can also say if determinant of A is not equal to 0, so A inverse exists. That's equivalent. Okay. All right. So now I'm going to show you a little bit of how do I use the inverse to compute the solution of linear equations. Okay. For example, if I give you two linear equations, one is 3x1 plus x2, the second one is 2x1 plus 4x2 equal to 1. Okay. Now we want to find a solution. We want to find out what is x1, what is x2, basically. Okay. To do that, we can write it in a matrix form. Okay, which is 3, 1, 2, 4 x1, x2 is equal to -1, 1. Okay. You sort of just put them together in a matrix form. Okay. Then what I do is, if I consider this matrix 3, 1, 2, 4 is by matrix A, okay, I can multiply both sides by A inverse. Okay. Of course, you left multiply. You don't do the right multiplication. So if I do A inverse on this hand side, A inverse times A, which is equal to A inverse times this whole A11. So what I will have here is this is just A inverse times A, according to a property. A inverse times A is identity, right? Which is just identity. Okay, identity. Where identity times a vector over here is still itself. Identity something is itself. Okay. So what we have here is the solution x1, x2 is just the A inverse times A11. So we just need to compute the inverse. When we compute the product, we'll get the solution. Okay, now let's take a look at the inverse. Now I'm showing you how to use the determinant method. So which is equal to 1 over determinant of A. This is C11, this is C21, this is C12, this is C22. Okay, let's do a C11. So C11 is -1, 1 plus 1. Okay, so this is 1, this is 1, so this is 1 plus 1. So this one is when you when you delete let me figure out right over here. When you delete A, remember you don't do this. When you look at AA is what? A is 3, 1, 2, and 4, right? So the saying is this one remaining one is because A is 2 by 2, so this matrix here is 1 by 1 because it reduced the one row and one column. So this is 1 by 1, which means a scalar. What you do is for C11, you just remove the first row and the first column. So what we get is 4. So it's 4 over here. The determinant of 4 is still 4. So it's -1 to the 1 plus 1 is 2. So -1 to the square is 1. 1 times 4, so it's still 4. Okay, similar way to C12 is -1, 1 plus 1. Okay, so which is -1. And then here is I'm going to delete the first row and the second column. First row, second column. So I end up have only 2 right here. So the determinant of 2 is still 2. So I have -2. You follow a similar way, you can get C21 and C22. I want us to repeat the same thing. Okay, what I have here is I just put a C11. Okay, it's 4. C21. So you should do C21. This is now C12. Okay, C21, which is -1 over here. Then C12, which is -2, and the C22 is 3. So do it here. So I'm going to just clean it a little bit. So this is the matrix I have. So determinant of this, determinant A is just the if I remember, determinant is the product of diagonal entries minus the product of diagonal entries for the 2 by 2 matrix. So it's 1 over determinant 3 times 4 minus 2 by 1. So this is 10. So 3 times 4 is 12. 12 minus 2 is 10. So 1 over 10 of this matrix. Okay, right here. So the solution will, for x1, x2 is right over here is just A inverse. In order to compute A inverse 1 over 10 times 4, negative 1, negative 2, and 3 times, this is 1, 1. Okay, 1, 1. So it's 1, 2. 1 over 10. So we do the product over here first. So product of this guy is this one times this column. So it's 4 times 1 plus minus 1 times 1. So it's 3. And this guy is negative 2 times 1, which is negative 2, plus 3, which is 1. So it's 1. So it's 1 over 10, 3, 1. So have 0 0.3, 0 0.1. So that's the solution. Okay. So this shows how to use a computer inverse and also how to use a matrix inverse to compute a solution to a linear equation.